In this related rates example, we have a radar tracking site that is following a plane that's flying in a straight line. At its closest approach, the plane will be 150 kilometers away from the radar site. So what we're imagining here is that we have a radar site that's tracking a plane. At its closest approach, the plane will be 150 kilometers away. Meanwhile, the plane is traveling at 600 kilometers per hour. Now that means if this is the closest approach, in this diagram, we would have the plane, say, moving down like this, moving south, and again, if we draw a different scenario instance during this process, what we'd see is the plane starting out fairly far away. Let's make that a bit nicer. And then the plane being right aligned with, and then the plane would actually end up below, on this diagram, the level here, or on a map, south of the radar station itself. What we have is a common rate. We have the rate at which the plane is traveling is 600 kilometers per hour. But one of the things that we're asked here that is new is how quickly is the radar rotating to track the plane when the plane is closest. So what we're interested in here is how quickly is the angle changing in this scenario. So imagine focusing in on here to here to here. There's an angle that's getting smaller, and it reaches 0 and then goes negative. That's fine. But how is that angle changing? Well, that's asking for d theta dt. The kinds of units that would make sense for that would be degrees per second, or degrees per hour, or radians per hour. We're going to use radians because we're in a calculus class, so we may convert to degrees just to make it a little more understandable. So if we take a look at that, and we also look at the speed of the plane, well, let's give this quantity here a value. That'll be the distance of the plane, and let's put this on our usual north and east axes here, plane north of the radar station. And what that's going to give us is dy dt is negative 600 kilometers per hour. This quantity here is getting smaller and smaller until it reaches 0 and then goes negative if we're talking about distance north of the radar station. So we have one rate, we want the other rate. Before we can get to how those are related, what we need to do is relate the quantities. And here we want to be specific. Y is changing and theta is changing. Those are the two I want to bring in. Well, if the theta and the y are what I'm most interested in, and I know that this 150 is always in here as well, and we always have a right angle triangle, you might be tempted to go with Pythagoras again, but as soon as we have an angle, we're interested in a different kind of relationship, and what springs to mind here is the y and the 150. Let's find the simplest relationship between those three, and the one that applies here is that tan of theta is going to be y over 150, opposite over adjacent. So that is a perfectly good relationship between the variables that we can start with to solve for the rates of change on the next page. So we're going to do the same thing we always do at this point, which is, because we're interested in time derivatives, time rates, we're going to take ddt of both sides of the relationship here, of the quantities. All right, the right-hand side is straightforward. We have y over 150. The 1 over 150 is a multiplier, and the derivative of y is dy dt, if we're taking the derivative with respect to t. Derivative tan theta, you might have to look that up to remember it, but it's going to be sec squared theta. But don't forget the inside chain rule. We're also going to take the derivative of the inside, and that'll give us d theta dt. Now that's a little bit ugly, so we're going to work with that a bit. What I'm going to do is replace the sec squared with 1 over cos squared. The calculator buttons only work with sine, cos, and tan, so let's turn it into a cosine. And that makes it even easier to work with, in fact, because what we're going to do then is bring this cos squared up to the other side, and it's going to become a numerator expression. So we'll have 1 over 150 cos squared of theta dy dt. And with that, at the point where the plane is closest, what do we know? Well, we said in the pictures that that was theta equals 0, and dy dt was a constant. It would be minus 600 kilometers per hour. And that fills in all the gaps here. So that instant d theta dt is going to equal 1 over 150 cos squared of 0 and minus 600 cos squared of 0, much better known as 1, and everything else here is minus 4. And here you just have to be careful with your natural units. The units of time that we're using were hours, and the theta, though, is by default going to be, because we involve derivatives, it's going to be the natural units of that derivative rule. Derivative tan of sec squared only applies when radians are our units of angle measurement. So we're going to be at negative 4 radians per hour. So it's actually a pretty slow process. Half a circle is pi, so it'd take almost a full hour for this plane to go around in the radar station as it moves from north to south here. And again, is that unreasonable? Not too bad. When we're that far away and traveling 600 kilometers per hour, it's not going to look like the plane is moving that quickly when we're that far away from it. So this seems like a not unreasonable value. Now, as a follow-up question, does that angular rotation speed up or slow down as the plane moves away? So imagine the later scenarios where we're measuring this angle. Well, you can use your intuition again, or we can look at the calculations. We have our 1 over 150 cos squared of theta and dy dt. This is a constant. This is a constant. So what we're asking is as theta increases from 0, so as it gets, we call it negative or positive, it doesn't matter, it's going to get squared away and the cosine doesn't care either. But as theta gets bigger from 0, what happens to cos squared? Well, cos of theta decreases. Think of a cos graph. The cos graph starts at its peak at 0, and then it goes down afterwards. We're never going to reach even 9 degrees here. So cos of theta decreases. That means cos squared of theta is also going to decrease. And that means out of all these terms, we have two constants and something that's going down. D theta dt is going to decrease as well. So it's going to turn more slowly. And again, if you think of your intuition about watching something go by, imagine a bird flying. Say you notice it when it's close to you. As it moves away from you, you'd have to turn your head less and less to keep it into sight, even though it's moving at the same speed in a straight line direction. You don't have to turn your head very quickly or as quickly as it moves away. And that's what, again, this mathematics is reinforcing with a nice explicit quantitative relationship between those two rates. So again, related rates problems, tying two derivatives together based on some relationship between the initial quantities that we are interested in, and then using calculus with implicit differentiation and the chain rule to relate the rates in another equation. A very powerful technique, definitely worth some practice before you get into an assessment on this area in the course.